to start off the day today with a practice question. This is going to be numerical response number 23, and it's on about page 13 of your worksheet booklet if you want to have a peek, okay? We'll give you about 2 minutes to see what you can do with that question, please. Let's have a look at the question. It says, at a coal mine, a train engine bumps an empty hopper car that has a mass of 10,000 kilograms such that it rolls at a constant speed of 2 meters per second under a coal storage bin. When the hopper triggers an electromagnetic switch on the track below the storage bin, the bin drops a load of 12,000 kilograms of coal into the hopper car. So you've got this little collision that's taken place back here where the train engine bumps the hopper car, although that's really irrelevant to our question, right? We don't care about that collision between the train engine and the hopper car. What we care about is the, for lack of a better term, collision between the coal that's falling down here and the hopper car that's moving right there with a velocity of 2 meters per second. Now, when we see this question, we see something moving to the right, something moving downward before the collision. It looks like this hopper car and the coal combination should have a momentum that's down and to the right after the collision. We're going to see in a moment here that it technically does have a momentum that's down and to the right, although in reality, right, in practice, it ends up going horizontal along the track. I'll explain that more in just a moment here. Okay, but essentially, this is technically a two-dimensional collision where the law of conservation of momentum in 2 dimensions, x component, y component, both apply here. We want to find the speed of the hopper car immediately after receiving the load of coal here. So let's break it down into an x component and kind of a y component, as you'll see in a moment here. For the x component, we'll say pi is equal to pf. We're going to say m1 v1i, that's the hopper car, plus m2 v2i, that's the coal before the collision, equals mvf. That's the hopper car and the coal combined after the collision. M1, the mass of the hopper car, is 1 times 10 to the 4 kilograms. V1i, before the collision between the hopper car and the coal, is 2 meters per second. This is 0, because although the coal is moving before the collision, it's moving on the y-axis, right? It's not moving on the x-axis. And right now we're analyzing the x component, so we're going to ignore everything y component. The other thing is we don't really know how fast it's moving either before it collides. Now, what's the combined mass? 10,000 plus 12,000 is 22,000, 2.2 times 10 to the 4 kilograms times VF. Solve for VF there. What do we get when we solve for VF right there? Thank you, Merrick. 0.909 meters per second. All right. That's the x component. That's how fast the hopper car and the coal are moving after the collision on the x-axis. Now, if we were to do the y component, where there is technically a y component, if we were to do the y component, go through that process, assuming we knew what the velocity of the coal was just before the collision, solve for the y velocity of the hopper car / coal immediately after the collision, we would find its velocity to be something like this. And so on. It would be so ridiculously small, the y component of the velocity immediately after the collision, that it just doesn't matter. So we don't need to do the y component. Now, how do I know that it's going to be that small without actually doing the calculation? Well, because on the x component, you have 2 things colliding. Right? You have 2 things that have the momentum immediately after the collision. The hopper car and the coal are moving on the x-axis immediately after the collision. But on the y-axis, you've actually got 3. The hopper car and the coal are moving on the y-axis. Can you tell me what else is moving on the y-axis? The Earth. You're pushing the Earth down as well, right? The Earth becomes part of this system on the y-axis. Now, can you tell me why that number is going to end up being so small? Yep. Good, good. So if you're going to have the same y momentum before and after, And the y momentum before is due solely to a little bit of falling coal. And the y momentum after is due to the coal, the hopper car, and the earth, which is not 10 to the 4 kilograms, but rather it's 10 to the 24 kilograms. Then the velocity of that is going to be so ridiculously small, right? It's like when we fire that gun and fire that bullet. Okay, the bullet goes off at a speed of 600 meters per second. The gun goes back at a velocity of like 1 or 2 meters per second. Why? Because they have the same momentum, and the gun is so much heavier. Okay? Well, if we have the same momentum of the coal just before the collision as the momentum of the hopper car, coal, and earth afterwards, then the earth is going to make it go so ridiculously small. Make sense? So listen carefully. If you ever have a question that's involving the earth as part of your mass for a conservation momentum problem, just ignore that component. That make sense? Just ignore that component, because the number, even if you could calculate it, is going to be so ridiculously small that when you combine the x and the y component into a triangle, you're going to get the x component. So what's our answer here? B times 10 to the negative w. That would be 9.09 times 10 to the minus 1. We're looking for the value of b, so we'd express that as 9 decimal 09, or 9.09. All right, let's take a look at the homework we had last night now. We had 495, the second question that we were working on in class yesterday. In addition to that, we had page 491, number 1 and 2. I'd like to do 1 or 2 of these questions of the 3. Okay? You tell me which ones you want to do. 495, number 2, 491, number 1 and 2. 495, number 2. All right. Got it? 491, number 1. Got it. If we really need to do number 2, yes, we will do number 2, actually. That's one that I did want to do, actually, myself. So we'll do all 3 of them. That's okay. Number 2 on page 495 says a 65.2 kilogram student on a 2.5 kilogram skateboard moves at 0.4 meters per second to the west. So you got this combined thing, student skateboard moving to the west. He jumps off the skateboard at south of west, and the skateboard goes off in some other direction. So he goes off in this direction, the skateboard goes off in some other direction. Let's draw this out here, okay? We know this is a collision, we know, or an explosion, right? It's a firing a gun, except it's 2 dimensions. It's an explosion. Conservation momentum applies, but we've got to deal with it in an x and a y component. And to do that, we're probably going to draw a diagram. So we got, let's say, a mass here of 67.7 kilograms going to the west with a velocity of 0.40 meters per second. That's before the explosion takes place. Now afterwards, let's call this my explosion point. Okay, my x is my explosion point here. Afterwards, the guy goes off 30 degrees south of west. Okay, that's going to be down here 30 degrees south of west. Okay, we're going to call the guy object number 1, 65.2 kilograms, and 0.38 meters per second. Now the skateboard is going to go, I think the skateboard is going to go this way with a mass of 2.5 kilograms. But I'll tell you what, because we have a leftward momentum, a westward momentum before this collision took place, or this explosion took place, it actually might go up here somewhere. That's possible. We don't know for sure that it's going to go up and to the left this time. We know it's going to go up, but we don't know for sure that it's going to go to the left. I think it is. And that's the way we're going to draw it anyways. If we guessed wrong, then it'll work out. All right. What are the first 5 words you think of when you see this picture? I don't like funny angles. So let's get rid of that funny angle then. Okay, somebody last semester, I said, the 5 words that you think of when you see this question, I don't like funny angles. I said, what do you do when you don't like funny angles? Somebody last semester says, kill it. So let's kill this funny angle. Let's get rid of this funny angle. Okay, take it over here. We got 30 degrees. 30 degrees right here. This is an X, this is a Y, and this is 0.38 meters per second. We're going to find the X component by the cosine function because the X component is the adjacent side of the triangle. Cosine 30 is equal to adjacent over 0.38. And we're going to find the Y component using the sine function. Sine 30 degrees is equal to opposite over 0.38. For X, we get 0.32909 meters per second. And for the Y component, we end up getting 0.19 meters per second. I'm just going to draw a little border around that just to remind me that that's not really part of the main part of my solution. That's just a little aside, the little taking the 30-degree angle out back of the barn, putting it out of its misery, getting rid of it, changing it into an X and a Y component here. Now, I could redraw this if I want. I could redraw this so that it wasn't down at 30 degrees, 0.38, so that it was over to the left and down. I'm not going to this time. Okay, I think we can work without doing that, but if you want to, please feel free to go ahead and do that. All right, X component. We're going to say PI equals PF. M VI. Why just M? Why just MVI? Why not M1 V1I, M2 V2I? How many objects do we have before this explosion takes place? Before it takes place, we have one object. It's a guy in a skateboard. They're one. He's on the skateboard, right? If he had a backpack on, part of the same mass. Look, we're not separating the guy from his clothes. We're not saying, oh, the guy is 64.8 kilograms and his clothes are 0.4 kilograms. Let's make those separate, right? The clothes are a part of him. So is the skateboard before the explosion takes place. MVI equals M1 V1F plus M2 V2F. There's two objects, though, after this interaction takes place. 67.7 kilograms times negative 0.4. Negative 0.4 because it's moving at 0.4 to the west. That's on the x-axis. M1 is 65.2 kilograms. Now here's the test. What's V1F? What's the x component of that 0.38 meters per second? Remember, we're never going to use that 0.38 again. That's gone now. What's the x component of that 0.38? Yep. 0.32909, except we're going to make it negative. We're going to make it negative because it's going to the left, right? Left and down, but we care about left right now. Object number 2 has a mass of 2.5 kilograms times V2F. That allows me to find the x component of the final velocity of the skateboard. We do that, we get 2.2493, negative 2.2493 meters per second. That's the x component of my final answer. When I drew my picture up here, I made an educated guess that the skateboard was going to go to the left and up, but I said I wasn't positive it was going to go to the left. Now I am, because I just got a negative value for the x component of the final velocity. All right, let's deal with the y component now. We're going to say the same thing for the y component, pi equals pf, but the initial y component, I'm just going to call it 0. Right away, I'm going to say it's 0. Why? Well, because the object is moving on the x-axis, and I know that it doesn't have a y velocity, so I'm going to say the y component is 0. There are two objects, though, afterwards, m1 v1f plus m2 v2f. 65.2. Anybody tell me what V1F is? We get V1F there, Terry? Good, and it's positive as well, right? It's positive because it's upward. No, sorry, it's negative. Negative because it's downward. So this one was negative because it was left. This one is negative because it's downwards. So if it's left and up, x would be negative, y would be positive then. M2 is 2.5. Solve for V2F. V2F is easier to find in this case. When we get it, we get 4.9552. So what do we do now? Physics 20, that's what we do now. We say negative 2 to the left and 4.9552 upwards. We find the speed by using the Pythagorean theorem, and we find theta by using the inverse tan function of 4/2. All right, let's have a look at question number 1 from page 491 now. This one says a 97-kilogram hockey center stops momentarily in front of the net. He's checked from the side by a 104-kilogram defenseman skating at 1.2 to the east, and he bounces at 18.5 degrees south of east. What's the velocity of the defenseman immediately after the check? Let's call the hockey center player number 1. Whoops. Player number 1. His initial velocity would be 0 meters per second. He was skating, but before the problem started, he stopped. So he's at rest when the problem begins. His mass is 97 kilograms. He's checked from the side by a 104-kilogram defenseman traveling east. So we're going to say object number 2, 104 kilograms, 1.82 meters per second. It's going to the east. Let's just move these numbers here. That's before the collision takes place. Now, after the collision takes place, let's say this is our collision point. It says the hockey center, it's checked, and the hockey center bounces at 18.5 degrees south of east. So the hockey center, player 1, is going downwards here at 18.5 degrees at a velocity of 0.940 meters per second. You can probably make a pretty good guess at where the defenseman's going to go, at least ballpark. Austin, where's the defenseman going to go? Good. So object number 2 is going to go up here somewhere, up and to the right. And this is what we want to find, right? Exactly where he goes with what velocity. So we see what we have drawn here. What do we think? What are the 5 words that come to my mind right now? I don't like funny angles. So we get rid of the funny angle. Take it off to the side over here. 18.5 degrees. This is X, this is Y, this is 0.940. Let's get the value of X and the value of Y so that we never have to use that 0.940 again. Cosine 18.5 is equal to adjacent over the hypotenuse. And sine 18.5 is equal to the opposite over the hypotenuse. Five three. 883. Okay. And this side, Mark, you got that? All right. Let's put a little circle around that just to set it off to the side here. And now let's go back to our actual problem, the meat of the problem here. X components, Y components. PI equals PF. M1 V1I plus M2 V2I equals M1 V1F plus M2 V2F. I wish these hockey players weighed the same thing. How come? What would that do for me if they had the same mass? Cancel them out, right? But they don't, so we can't cancel them. Object number 1 has a velocity of 0, so we'll cross that off. Object number 2, 104 times V2I is 1.82. Okay, all of his velocity is horizontal. M1 is 97. V1F. This is the challenge, right? Do we get this? Alan, you get what V1F is there? V1F, object number 1, X component. Nope. Object V1F, object number 1, X component final. I think it's 0.883. Anybody else get 0.89 for that? Yes, so it's not 0.883? Okay, let's fix that up then. Dallin, what'd you get there? 0.889? Okay. All right, so you're right then, let's replace a V1F with 0.89142. M2 is 104 times V2F. V2F is 0.98857 meters per second. That's the X component. The Y component, PI equals PF. The initial Y momentum, once again, is 0 because everything's on the X-axis. M1 V1F plus M2 V2F. What's V1F? Pick. Yep. Yes. Yeah, it is. What's V1F, somebody? Ali, what's V1F here for the Y component? Good. Negative 0.2983. Negative because it's going downwards. So we had a positive X, but a negative Y. Positive X because it's going to the right. Negative Y because it's going downwards. Negative 0.2983. Plus M2 is 104. V2F. We'll find that. We get 0.27822. And then, of course, we combine them, right? 0.98857, 0.27822. Solve for V, solve for theta. All right, let's do that last one, which is number 2. It's a little bit tricky, actually. So it's a 1,200 kilogram car attempting to run a red light. It's not really a car attempting to run a red light. It's a driver attempting to run a red light. Strikes a stationary 1,350 kilogram vehicle waiting to make a turn. Skid marks show that after the collision, the 1,350 kilogram vehicle moved east of north. The other one moved west of north. Uh-oh, I don't like this. We get 2 funny angles. What was the velocity of the 1,200 kilogram car just before the collision? Let's draw it out here. Let's say the stationary car, we're going to make car 2, 0 meters per second, 1,350 kilograms. The 1,350 kilogram car after the collision goes east of north with a velocity of 8.30 meters per second and an angle of 55.2 degrees. The other car, car 1, goes off this way with a velocity of 12.8 meters per second and an angle of 36.8 degrees west of north. Which way was car 1 going before the collision took place? Well, I think it's pretty safe to assume that car 1 is down here somewhere and is going up this way somewhere. Are we told that it's going straight north before the collision? We're not, are we? That's kind of what it looks like, I'm assuming, but I'm not. Okay, I'm drawing it like this. Okay, I think it's going to be close to north, but we don't know that for sure. We're going to draw it like this, then we're going to figure out exactly where it's coming from, okay? Now, we got 2 funny angles here, so we got to get rid of both of them. Let's take them off to the side and do that. Here's number one. It's got an X and it's got a Y, and it's got an angle of 36.8 degrees. We're going to say cosine, for X component, we're going to say sine this time because it's opposite. Sine 36.8 degrees is equal to X over 12.8. Cosine 36.8 is equal to adjacent over 12.8. While you guys are calculating that, we'll go to the other one, do that one as well. This time we have 8.3 at 55.2. Sine 55.2 equals opposite over 8.3. And we'll say cosine 55.2 is equal to adjacent over 8.3. 10.24936 meters per second. What was the X component of this one? Haven't got that one yet? Okay. Y component of the first one? That's the Y component of the first one? All right. 7.66. Thank you. And the Y component was 10 point. Okay. And the X component of the second one was 6.81. Thank you, Terry. And the Y component was, Eric? All right. Are those right? All right. Let's put a little circle around those to indicate that they're the resolving of the components here. It doesn't form the main part of our question. Now let's go deal with this, okay? X component. M1 V1I plus M2 V2I equals M1 V1F plus M2 V2F. M1 is 1,200 kilograms. Now, we think that this is going to be on the y-axis only, but we're not told that, so we can't assume it. Multiply that by V1I. We're looking for the X and Y components of V1. Object number 2, we know it's at rest before the collision takes place. Now it gets trickier with these components here. What's V1F? V1F. 7.66? Positive 7.66. Right? We got rid of the 12.8 and we replaced it with 7.66 and 10.249. M2 is 1350. And the X component of object number 2 would be negative 6.81. Negative because it's to the left. Object number 2 is going to the left after the collision. Look, object number, or is that right? No, that's wrong, isn't it? That's wrong. Object number 2 is positive and object number 1 is negative. Is that right? See, this guy's object number 1 is going this way, so it's going to be negative 7.66. And object number 2 is going to the right, so it's going to be positive 6.81. We do the math there for V1I and we get 0.00125 meters per second. All right, so the x-axis, this car before the collision is moving at 1.25 millimeters per second on the x-axis. So we were saying before we drew this, we think it's going to be just on the y-axis. It effectively is, right? If it's moving at 1.25 millimeters per second. Let's do the y component and just compare the values. I think we're going to find the y component is much, much bigger. All right, M1 is 1200 times V1I plus 0 because the second car is at rest again. This was object number this was object number 1, right? And this was object number 2. So object number 1 has a y velocity of 10.249. Object number 2 has a y velocity of 4.7369. We do that, we end up getting V1I is 15.578 meters per second. All right, so it's moving at 1.25 millimeters per second on the x-axis before the collision and 15.5 meters per second on the y-axis. Does the x-axis really matter here? Not really, right? You draw this triangle, this is what it's going to look like, something like this. Here's the x-axis. It probably goes even further. There's the y-axis. What are you going to get for a hypotenuse when you do that triangle? 15.6, right? What are you going to get for an angle? 90 degrees. Really, it's straight upwards, right? It gets so close to 90 that it's going to round to 90. Okay. Now, you ever wonder, like, oh, is it big enough that I can ignore, big enough of a difference that I can ignore one of the components? Well, don't ignore it. Do it. Do the math involved. But I think most of us can see the big enough difference here that we don't have to bother with that.